Certified network professional instructor. He is currently associate professor in the Polytechnic University of Valencia. He is the chair of the Integrated Management Coastal Research Institute, and he is the head of the Active and Collaborative Techniques and Use of Technological Resources in the Education Innovation Group. He leads many national and international projects. He is currently the chair of the working group of the standard IEEE 190.1. I request sir to begin the session.
Well, hello. My name is Jaime, and my surname, we in Spanish people have, and Latin American people have two surnames, is Lloret Mauri. I generally use my first surname for all my publications. This is why some of you have asked about the surname. Well, this is Lloret, the first one. The second surname I generally don't use for publications. Well, anyway, I'm also belong to IEEE. I'm IEEE senior and also IRA fellow. And currently I'm the chair of the Integrated Management Coastal Research Institute, which belongs to the Polytechnic University of Valencia. I have been chairing the Internet Technical Committee, which belongs to IEEE Communication Society and IEEE Society. IEEE Society, sorry, to Internet Society. I'm currently chairing the standard IEEE 1907.1, and I'm editor of several international journals, such as Ad hoc and Sensor Wireless Networks, which is indexed in I.C. Thompson, and Network Protocols and Algorithms, and International Journal of Multimedia Communications. I am currently involved in several international conferences. If anyone of you want to know more about me, all the publications are in Google Scholar, so you can find our last research. Moreover, at the end of my presentation, you will see a list of publications which I have used to prepare all my slides. The first thing we need to know is exactly what is a smart city, and then I will try to introduce our research on this topic. First, how to achieve or how to know a city is smart, or how to have a smart city. The first thing we need to know is there should be some type of data gathering, and this is done by sensors. We need sensors to have a smart city. We need something that gathers data. The second issue is we need some protocols and algorithms to transmit this data through the network and to have it and even see what is happening. If we don't have a data transmission system, we don't have a smart city. And finally, we need some type of artificial intelligence, otherwise the city is not smart. How we achieve this intelligent city? Because there should be some algorithm, some type of data treatment to achieve this, to make it smart. Basically what we have is that one. Many sensors in the buildings, in the city, communications protocols that can be, that is used to transmit this data through any type of network. Can be cellular network, a wireless sensor network, it can be a wired network. And finally, a database which has some kind of artificial intelligence. All my presentation is going to be related with these topics, and I'm going to show our research contribution in each one of these topics. In order to achieve this, what we really have done is to create a research which has 4 legs. The first leg is the telecommunications part. Data communications. It's mainly our contribution here has been how to transmit data, how to have efficient protocols, efficient algorithms to have the data finally at the end side. Then we need to gather data from the environment. So we need people that is able to build some type of devices that are able to gather data from the real environment. Then we need another leg that is focused on computer science, concretely in artificial intelligence part, because otherwise we don't have smart decisions, we don't have a smart system that is able to take the most appropriate decisions for each case. And at the end, we need some type of people working in the real environment, in ambient engineering, in marine science, if there is a coastal zone, if any type of people working in urban areas, architectures, anyway. Well, the research is really from one side to the other, and it can start from any type of leg, any of these ones. Well, the outline of my presentation is this one, sensors and wireless sensor networks, initially. What have been our contributions in this part. Then I will talk about communication protocols and algorithms, and finally about artificial intelligence applied to big data. Well, in the side of sensors and wireless sensor networks, not needed to be wireless, but is because of their type of the benefits. Wireless used to be the most appropriate one in many cases. Well, we have developed many things. First of all, we have developed real sensors that are able to collect data. The first thing we have to think is, if we need to gather data from many places, if we need to, we are going to have many sensors placed in all the urban area, we need cheap sensors. Otherwise, we cannot develop a big wireless sensor network. So our main purpose was to develop very cheap devices. From one side, the real physical sensor that gathers the data from the environment must be very cheap, and also the sensor node. Well, our efforts have been focused on those issues. If the sensor node is going to be very expensive, we are not going to develop a wireless sensor network. It's very expensive. If we are able to develop very cheap devices, very cheap physical sensors, we are able to have many sensors in the urban area. So our first purpose was to develop real sensors that in some cases are not too much accurate, but this is not the issue. We really need to know approximately the values, which will be useful to take some decisions. For us, it doesn't matter if it's 0.1 grade more in temperature or less. We need to know the temperature. This is the accuracy of the temperature. This is not need to go very accurate, at least for us. Also for animals, and like the sensor, maybe the humidity. It's not needed to know 0.0001 of humidity. It doesn't matter, this type of accuracy. Maybe 0.01 is enough. And this decreases very much the cost of the sensor, the physical sensor. If we want thousands of sensors, the most important is to have a very cheap physical sensor, and also the very cheap physical node. So this was our main purpose. We developed several physical sensors, and initially we used real nodes that were available in the market, and then we tried to decrease also the sensor node as much as possible. We are able nowadays to have a physical sensor plus a node less than €5. So it's, if we want to have thousands of nodes, it's okay. One of our main sensor nodes has been FlyPort, but we have been using many of them. For FlyPort, we have been developed many things with FlyPort. This is one of our main architecture, using FlyPort for building and monitoring. Using very also regular in the market Linksys access points, and this sensor node, FlyPort, we developed a system to monitor houses, mainly in the cities that are very close to sea, because they are affected very much because of the humidity of the sea. And well, one of our main contributors has been to develop sensors and monitor the state of the buildings, mainly old buildings, because they are more affected by this type of things. We have also developed systems to monitor mangrove forests and also areas with rivers, with lakes, that are mainly affected by the type of water is coming and the type of animals or fishes are inside. So at the end, we developed a system using flyports to monitor a system, and finally security systems to let us monitor remotely from internet and so on. One of our developments have been in Spain, well, to monitor the difference between fresh water and the sea, just because of the variation affects very much the fauna and flora of that place. So we needed to know exactly what is happening in the salinity values in estuaries. So we develop sensors, cheap sensors to monitor these type of things. Well, we also use Wii Remote, which is from a Spanish enterprise and also well known outside Spain. And also, it's very small, and also, this battery lets you work with it even 1 year. So it's good because of it is we are able to put it in one place and forget it for 1 year. So it's good. This is one of the other issues. We need cheap, and also to not keep maintaining it constantly. You can leave it there and 1 year transmitting information. This is good. We also developed this system, the same system, but we applied it to another place to monitor for cooperative monitoring of pharmaceutical products inside the urban area. So it also was another type of application. So it was important because in Spain we have many. It could be cold days, but it could be very hot days. So the pharmaceutical products could be affected because of this type of variation of temperature. And also to deliver fresh products, like fish, any type of meat. So at the end, if we don't keep them cold, they are affected, and the product, the quality of the product is affected very much. Well, this has been some of our last developments on the left side, and one of the systems we are now using is Arduino with Atmega 328 microprocessor, which is very cheap, and we are also using for as a sensor node, and we are adding to it sensors, physical sensors developed by us, and well, a very cheap system to gather data. Well, this is some of our systems we have been using to monitor information, to gather data from the real environment, or even to take information from the refrigerator. I know if the refrigerator is too much cold, too much hot, the door is open, or it has nothing inside. We are able to put it inside and gather sensors. With sensors, take this type of information. One of our applications were really to put these type of sensors inside some household appliances like wash disher, like a refrigerator, well, also oven, and so on. Well, we have arrived till one of our main contributions, that has been, we are able to put a lot of sensors inside a house, and we are able to gather data from the house. We are able to monitor if something wrong is happening inside. So the people that can be benefit from this is old people and disabled people that are not able to move or need some help at home. So at the end, if we are able to develop many sensors and put it in the house, we can help them in their lives. And one of our last research, well, 2 years ago, we proposed a system that was able to gather this data, treat this data, take some decisions, and finally, so after these decisions, some actions inside the house. For example, one of the issues was, well, let these old people go to the room. If the system is monitoring his movement, and he's going to the room. If he goes to the room opens the light. It's okay. But what happens is, goes to the room, but finally doesn't go inside the room, just it goes very close to the room to take something. Well, the system learns from the behavior of the old people, see what is happening, and if finally the person doesn't go to the room, this person only has to check and say, no, I'm not going to go to the room. And this behavior is learned by the system, and after some time, the system is able to decide if, because of this behavior, is going to the room or not. So this learning system is able, what is happening if some person is sit down and finally is going to sleep. Well, the system is able to learn that he's sleeping and close the light or switch off the TV. So it's able to learn as well as this person has to say, okay, I'm going to, the light is open. Do you want to keep it open? No. No. The system is learning. The system is learning of this type of behavior. At the end, you have a smart home that is able to help you in your life and assist you living. Well, another issue, another topic we have been working on very much, developing communication protocols and algorithms. Well, all of us know current type of protocols and algorithms are very used nowadays. Well, it's GPRS, GSM, UMTS, LTE. Well, another type of for more local environment, Bluetooth, Zigbee, Wi-Fi, WebEx. Well, at the end, all of them can be applied to technologies like Internet of Things, machine-to-machine, device-to-device systems. Well, what we really have? Well, we have sensors, cameras at the bottom, several type of technologies like wireless sensor networks, wireless mesh networks, wireless outdoor networks that are able to communicate these type of devices. A technology in the upper side which allows device-to-device communication or machine-to-machine or even sensor actuator to directly take decisions. But how these decisions are taken? Because there is an artificial intelligence system that is able to take decisions because of this knowledge, this training, using training systems, learning systems, and the decision algorithms. They must be the most accurate as possible. Well, what happens if we have a system that is being used for a healthcare, for example, was someone has to tag this information, has to be in charge of be sure that this type of information is accurate and the most appropriate. Well, finally, we have some actuators that are the ones to take these actions. Well, from the perspective of communications protocols and algorithms, we have many. We take this, how we split all the communication part. We have direct connections between devices. After this, we have, for example, smart meters that can be used for water monitoring, houses, or for example, power electricity at home monitoring. And then we have a level 3, which is used for take this data to and send it to the server that is going to have a smart system. Well, this type of communication system is commonly used for data gathering, power electricity data gathering, or even water data gathering from the entities, operators like water operators and even electricity operators. We have developed along the years several algorithms to, to have monitoring, for example, electrical house appliances, also smart communications architectures for ambient assisted living, and well, even we have had systems that how to communicate electrical grids, smart grids, and how the electricity must be moved inside the smart grid to provide or to predict the power consumption in several parts of the city and decide where is going to be more consumption and provide more power consumption at some time of the day. Well, at the end, this cannot be possible if we don't have smart systems that are able to, artificial intelligence, taking this data and trade this data and take the smart decisions. So we have developed several type of systems. This is one of machine learning diagram for smart continuous e-health monitoring, was one of our systems where main contribution was to know exactly the most important parameters to be measured, to put it inside our smart or machine learning algorithm, and finally to know exactly if something is happening or not, and if we have to send an alarm or not. We also develop a big data architecture for electricity, water, and gas providing, and also because it's not a question of knowing how much is consuming each person or each family in his house, which is the most important issue for the operator. The important issue is not to have leaks or not to have water. These systems allow you to know if some water is being lost along the path from the provider to the house. So this is important because these systems is able to know that it is being lose too much water than expected and something is wrong in the system. Well, after some algorithms and even artificial neural systems, we were able to, taking this information from 1 year, able to predict the amount of electricity that is going to be consumed next day. So if we know exactly how much electricity is going to be consumed next day, and even where, we are able to provide enough electricity along the day just for several parts of the city and avoid suddenly peaks or suddenly having any type of electrical system fell down. So as an example of this was one of our main contribution on smart grids and power electricity prediction. We were able to know exactly the most approximately what's called the line for in many type of possible lines along a year. This was our prediction for next day, and we have been able to achieve even a mean error of 2.40% in 730 days tested. So it's quite good, only very few error percentage. So just to show you some of the data gathered, we were able to introduce in the system if it's a holiday day, if not, if it's a Monday, Tuesday. This type of information is help us very much to have this type of predictions. Well, even for water, we are able to know if someone is still living in one house or not. Or the most important, suddenly the persons are in holidays, they are not at home, and someone or something is wrong because water is being wasted. So something is broken, something is, there is a leak, so something, so we are able to predict these type of things. We have been tested this in a real environment, and well, for example, this is for 1 year, what happened, these people were in vacation during this, go outside their home. during summer. Well, we are also able to manage if something is happening in patients and send, for example, continuous health monitoring for those people that had chronic illnesses, and also for children monitoring, with chronic illness monitoring for children, what happens, how to have them control and avoid the main problems. Okay, all of this information I have shown, it has been taken from all my papers. So if you go to that Google Scholar webpage I told you, you will see almost all of them. I'm not going to go in depth to all of them because maybe will be so much time. So this has been also, all these publications have, are the background of this information provided to you. And, well, it's available to any one of you. You want any of them, I can send it to you by email, no problem. And, well, it's important to know that smart systems can be applied. Good. Yes, good. Smart systems can be applied to electric, water, and gas consumption savings, discovery or loss of water, gas, and power, even to have more efficient energy consumption, and even to monitor buildings, bridges, historical constructions, because it's important to not to be safe, and maybe some of them can fall down. You can try to monitor them, avoid this type of effects. And, well, also it can be used for location and tracking, and also for remote monitoring of patients, which is one of the most, of the main lines nowadays for this type of systems. So, well, sorry for not being in depth for my papers because there are very much, but if any of you want to any of those papers, just send me an email and I will send it to you. You can read all of them. And that's all. I hope you have enjoyed my presentation. And you have any question, I am free to answer it. Thanks.
Now I would like to invite our second keynote speaker for the day, Dr. Janet Light, Professor, Department of Computer Science, University of New Brunswick, Canada, to talk on automation in health monitoring.
Good morning, everybody. I hope we are feeling a little bit hungry. My talk I prepared for 60 minutes, but I'll cut it down to 30. So if I'm running through slides, don't worry. I'll make sure that you get something from it. So automation in health monitoring, this is the topic that I picked because mainly of the work that I do, applied research in health monitoring. So the talk overview, I would talk a little bit about the need for automation, especially in healthcare. Some statistics I'll give you, more on the North American side. I couldn't find much on the Indian side. Maybe you will have to go back and dig a little bit deeper to find. And then some of the health monitoring types broadly, and how the mobile healthcare has changed the whole scenario. Some of the challenges and solutions in automating health monitoring. Why do we need automation? Healthcare cost, some of you must have, not some, all of you must have felt of somebody falling sick at home and how much it costs you to take somebody to the hospital. And if they have chronic diseases like diabetes and Alzheimer's, then you can't count costs there. It is expensive. So to avoid expensive hospital care, then you're in a scenario where most people are working and you don't have the time to stay home and take care of elderly parents or grandparents. So you want them to stay healthy, safe, so you're looking for assisted living conditions. So you need automation there. The previous keynote did mention about it. Now, there are ICT, information and communication technologies we use. It's funny, we use them for so many of our personal stuff. Sometimes, we fail to use for healthcare, which could save a lot of money and time for us. So it is the right time we start using it. And there are tools that automate flow of information from hospital to the patient and vice versa. They are in demand. They are in high demand these days because you meet with a patient and you do not know their background, their history. It's hard to diagnose or treat a patient. Then the computing paradigms that are mushrooming, like pervasive computing, ubiquitous computing, body area network, wireless sensor networks, Internet of Things, cloud computing, AI techniques, so many, and never know what's going to come in the next few months or few days ago. They make communication seamlessly possible even under harsh conditions. So it is time that we can look for a healthy, affordable ecosystem where we can have a better, healthy life. Okay, so automation helps. So this is some statistics that I brought, mostly from Canada and US, where I am familiar with. So the diabetes, you would notice that in 2015, it is 3.4 million, which is 9.3% of the population. And in 2025, it is estimated to go up to 5 million, which will be 12.1%. The reason it's not too it's not peaking so high is because there's the awareness and people are trying to maintain it. Then you would find the Alzheimer's disease. Here in 2010, this was around 500,000 people. Remember the population, Canada is second largest country in the world, but it has only 33 million population. So among that, there were 500,000 Alzheimer's in 2010, and it rose to 757,000 in 2012. It's not the number that matters here. You look at some of the numbers here, it's in terms of dollar values. So here you find 56,000, the one that I have brought in. They are people who are Alzheimer's and in hospital. In-hospital treatment is not a good place for Alzheimer's. You know, they have the habit of wandering out. So it is very dangerous, but still, because there's nowhere else, nursing homes are full, we have so many in the hospital. And then there are 564,000 with dementia, that's Alzheimer's. And in 15 years, it is expected to go around 1,937,000. It's not only the people that are affected, but the family that's affected because of them. So it's around 1.1 million, and the cost is 10.4 billion per year to take care of them. Now, this is some quick facts about United States. If you look here, in 2017, the Alzheimer's dementia cost to maintain them, it's $259 billion. And it's going to go up in 2050 to $1.1 trillion. So that is the cost of taking care of Alzheimer's in US. So this is the current cost, 259. It's a big number. Overall, diabetes, you have some percentage. I brought this slide because Asians, Indian Asians are there. 13% of them are Asian Indians. There is even breakdown of different. So you have to look out for us. If, you know there are so many people in your own home with diabetes. So this is something I brought, real values from my own province. So we need to cut the healthcare costs because of the rising in chronic diseases like diabetes and Alzheimer's. Also the cost of hospitals. Also shortage of good healthcare professionals, the mobility of a living life, the modern lifestyle that we have, and as more people, there's overall globally, you will find there's an increase in lifespan. So there's more age people, that means there are more diseases. As you grow older and older, you tend to get more diseases, so there's increase in healthcare cost. This is from my province that I brought. I live in New Brunswick, Canada. So there is a decline in population, and there is increase in elderly population. Because of this, there is a threat to even sustainability of a system, because 45% of the province, New Brunswick budget goes to healthcare. So just imagine. So building roads, maintaining infrastructures, so you have to choose between healthcare and the other expenses. It is, for an elderly, they spend around $72,000 per year for the elderly care. This statistics is 2-3 years back. It would have gone up higher now. So this is the province, and our population, if you look, New Brunswick, it's expected to go 22.2% elderly population. It's going to grow. So technology as an enabler, the previous speaker did talk a lot about number of technologies as for smart cities, but ICT, you can improve electronic health. It improves the healthcare delivery so that you can reduce duplication. You can avoid errors. You can increase the diagnosis time quickly. You can find the diagnosis. You can reduce treatment costs. Instead of taking multiple tests, you can go with single test. So also mobility supports care. Wireless sensor networks allows remote capturing of data, so you can, even if your parents are at home, if there's nobody to take care, if you have sensor networks around, they should be able to take the data and send it to the server, wherever the service provider, and you should be able to process it. There is also the ubiquitous pervasive healthcare condition, so anytime, anywhere, I'm away from my own place of living. So here, if I need healthcare, I should be able to access some of the data. Remote and continuous healthcare monitoring possible, digital hospitals, smart homes, so something the previous speaker talked, probably I could skip. So the health monitoring types, it could be wearable ones, but you also want to be non-invasive as much as possible. You don't want to have a big, bulky device hanging on to you, which is not usable. So as engineers, as scientists, when we research, probably we should always look for solutions which are usable too. So that is something that is closer to my heart. When I do research, I do work with those people who are involved in that particular area, so that the research is closer to the usability. Now you could be in ambient situations around you. So the choice depends upon the accuracy and the measurement, accuracy of the parameter that you are measuring. For example, if you are, previous talk we heard about sensors, but if you are measuring medical data, you better be careful what you are. You cannot tolerate errors there. Especially when, for example, if you have an automatic insulin pumping machine, if the value you read is wrong, it could kill you by feeding in wrong. So you have to be very careful with the device that you choose. That is something, and it's also usability. So I'm going to give you some, talk about some healthcare monitoring projects that my research team has been developing and being involved. One is the 911 EMS emergency medical services. In India, you call it 108. Some elderly care. I did a lot on fall study because elderly people tend to fall. I did some on sleep monitoring, and I'm going to talk a little bit about it. So the 911 emergency call, once there's an emergency, you call the number 911 in the North American, Canada, US. Here you have 108. It goes to the dispatch center. And then an ambulance or fire or sometimes even both are dispatched based upon the incident. Sometimes if it is a crime scene, police are also dispatched. So in such situations, you need data. So what we did, we collected the data from those remote sites and we sent it to the hospital, the clinical system. The beauty of the thing, we were the first to develop it, and the beauty of the system is we send it using clinical document architecture, CDA, HL7. So the electronic health standard, that is the one that is gonna help us reduce the healthcare cost I mentioned earlier. So if you want to go there, then our system should be connected to HL7 system. So that way, both-way communication is possible. Suppose you find a patient who has passed out, you do not know whether it's due to diabetics or due to heart attack or due to stroke. So if it is stroke, the first hour is a golden hour. So what treatment to give, unless you know their history, their background, you cannot. So this system brings both-way communication from the hospital, the patient history, and from here, vital signs. So if the patient is being transported, it helps the hospital to be prepared to receive. Otherwise, they would be waiting for the patient to arrive, and then they look for the blood samples and so on and so forth. So it saves a lot of lives. This is one of those screenshots that we developed. In fact, this we commercialized, and we have launched in India, and we do have clients in Coimbatore using it. So what we are doing now, as they respond, it's not only the paramedics, also police, also fire services and other services. Sometimes if it is a terrorist attack, then it's Homeland Security. There are quite a number of different organizations involved. So, but they never talk with their systems do not talk with each other. So the challenge here is the interoperability. So we have been working on those interoperability issues, and we have been using some standards, developing some standards so that the systems could talk to each other, because there's valuable information from other systems that would be useful for particular incident. Especially when we are going through a global secure systems, this do make a lot of sense. The other project that we have been working on for quite some time is the elderly monitoring. In the previous talk, we did see a screen, something like this, so I'm going to skip it. So the one we did, we came up with minimally invasive fall monitoring system. So we worked with some companies that had already existing fall systems. So they had quite a number of monitoring systems in their place of residence. These are the ones that we developed. So I'll give you the list of what we were monitoring. You'll be shocked what we do. Did the subject leave his room or her room, the time left and the time returned? If he or she left after sleep hours, if so, then they would send an application to whomever, whether it's relative or caregiver, saying so-and-so left. Okay. So also bowel movements. If they went to washroom, toilet quite frequently, there's a floor pressure sensor. So that shows that there's something going wrong with their systems. So a fall from bed, they already had some pressure sensors, bed pressure sensors. We developed our own. Then unusual behavior, again fall from bed, and sometimes they get agitated, especially if they're Alzheimer's. Pill medication, there's a pill box with a camera that keeps track of whether they are taking their medications regularly. And emergency situation, there's an emergency button, but you would be surprised. We talked to the patients there. None of them ever used it. You find solutions in market, alert button. When you fall, press the alert. They are so scared, they don't even press it. So there are so many useless solutions in the market, but there are. Then movement monitoring. We came up with these new solutions. One is for both of them mainly for fall detection and prediction. The first one we used Accelerometer, we used Shimmer. This is developed by Harvard Sensor Lab, and our team worked along with them. They developed it for Parkinson, epilepsy, stroke, and other movements. We developed it towards elderly fall. It's a wonderful system in the sense, not because we developed it, because we got 100% detection. And the best advantage of this is this could go on for 12 hours continuous monitoring. You can have a wonderful system, but if the sensor is constantly to be recharged, who wants to do it? Who wants to recharge a battery every 5-6 hours? So this was really good, and it even went up to 12 hours. So in our fall study, what we did, we identified the real fall. This is a real fall. These are fall-like activities. Suppose they sit firmly on their couch, you don't want to report as a fall. So if they sit on elastic surfaces or couch, so these are activities that they normally do, but they are not necessarily fall. So we identified them. It's also being patented in Europe. And so we identified what is real false so as to avoid false positives. We came up with the architecture and it was tested. The next thing we did was sleep monitoring. It's funny when, the reason we started this monitoring was because I thought if we capture the brain signals, because brain gives directions to the body, we should be able to predict fall. That's what I thought. And maybe it's true, but when I started doing the study, it didn't go that easily. It was easy to capture brain signals, but to predict, our MATLAB wouldn't work that fast, our system wouldn't work that fast, and so while we were doing it, we did end up getting some interesting results on sleep monitoring. Why do we need sleep monitoring? The sleep monitoring, you get the brain patterns more clearly. And the fall that we were studying with some of the elderly, we noticed that 50% of the falls take place during night when they sleep. So we thought, okay, let's capture their sleep brain signals. So this is the device that we used. That was the Spanish process. This is from Spain, Enobia. This is from Star Labs, Spain. We used this device to capture EEG. Brain has activities. I hope most of your brain signals are beta waves now. I hope. And I hope they are not delta waves. When you are active, when your brain is active, you get beta waves. And then when you sleep, it slows down, then it goes to alpha, theta, delta waves, slow. I hope none of you are in delta now. So this is a fall data. See, brain clearly shows fall data. Beautifully, we could capture the fall data. Okay, so the sleep, my intention was to find out when will the fall happen? You hear a lot of people saying, I saw dreams as though I was falling down. You hear all the stories, so I wanted to find out which stage. So we did study through the sleep stages. It has REM, non-REM. I'm going to go quickly so that I'm not taking a lot of your time. But it has stage 1, stage 2, stage 3. Earlier it used to be 3 and 4. So stage 1 is when, you start getting a little bit sleepy. And stage 2, you get the brain recuperates itself. You find lots of spindles and K complexes when you sleep. That's why people say your sleep is very important. Youngsters who are not sleeping, remember this. If you want your brain to stay young, you need that. Okay, so stage 3 is when you go into those slow waves, and then it starts repeating again and again. Sleep is a beautiful thing. You should study. I used to sit in front of my students, observe. It's beautiful to watch. Some of the signals. So this is the early stage, beta. This is when you're the slow stage, when you're sleepy. This is spindles, when you get those recuperation, stage 2. So my plan was to find out which stage is prone to fall so that I can study during that stage of the brain signals. I wasn't too successful in it, but we came up with some very good predictive, fall predictive, but they were not too quick enough, as I thought. Like if I captured the brain, and it's funny, I worked on it for 4 years, and now a US university, Dexter, they have started trying. So they said they'll send the students. I said, don't waste your time trying because I tried and didn't work. But they're still trying. Let's see if something comes better out of it. If you can find from your brain signals, if you can predict what is going to happen within the next half an hour or next 1 hour, great, kudos. So the EEG signal components, there are EEG labs, tools that can help you. So this would tell you how much of high frequency. So this is frequency 10. You had this much signal. So you can find out, there are tools that are available that can help you with that. So we use this to predict, as I told you. So we used SVM, data capture, communication, and then you have the algorithms to clean out all that, and then do the data mining. So we used SVM. This is how the signal looks like. So this is EEG data in microvolts. The flag tells you whether it's a correct data or whether it's a wrong data. Sometimes you get invalid data. And that's a timestamp. It don't look strange to you. It's from 1970. They start counting, and it's in milliseconds. So that's timestamp, one after the other. So we used SVM, and we used some of the data to train. So this is, 30 days, I had my team in a nursing home, and we had put our devices on Alzheimer's people. I thought if we can find for Alzheimer's, we can do for anybody. So we had 30 days, nothing happened. The day then I said, okay, let's take it out, because it was hard going behind these people all day and night. The day we took it out, one lady fell and we missed the data. It is hard to find real fall data of elderly. If some researchers are saying we got it, I really appreciate it. It's very, very hard. So what we did, we pushed a student. In fact, I had a summer student from India. We pushed him, and sometimes we did voluntary fall. Of course, we had padding on the floor to make sure he didn't get hurt. So this is some of the data, pushed fall data that we got. We wanted to make sure that the tools that we come up with are working with the real data. So we used, these are SVM results. So see, you would find, we also made him to go to sleep a little bit and then try to fall. So we did involuntary for data, but we also did voluntary push data. So we used some of them to train and then classify. And as you know, SVM works really well, so we got very good results. So it identified all falls. So knowing that all this are there, these tools are there, technology, wireless technology, with sensor networks, remote monitoring, all this could be put together for automation. So there's no limit at all. So there were research areas that we could, if you broadly classified, often it's the data collection point. It's really messy, it's not easy. If people say it is easy, no. Data collection point is very messy. And remote data communication, that is another communication protocols. Earlier talk we did see. And security. Even in the inaugural, the chief guest mentioned about security. It's interesting that, when you talk about security, confidentiality, authentication, message integrity, accessibility, availability, these are some of the jargons that you hear a lot. And for healthcare, you really want to, because you don't want, people can be malicious too. They could even send some wrong data and they could cause some major critical conditions, right? So security is very crucial. But as I told you earlier, usability, it's a problem. This is, Alice and Bob talking, and then you have the crypto algorithms, you have public key cryptography, symmetric key, hash functions, all this. But if you, in reality, none of them would work, especially in wireless media. Wireless, YEP, that the wired equivalent privacy, is very low security. So none of them would, this that we talk about, the high security algorithms, none of them would work. In our case, we were studying in continuous monitoring. So if somebody, for diabetes or whatever, we are continuously monitoring somebody. So if we use any one of those cryptographic algorithms, none of them would work. Interestingly, I should say, that student was from Madras, Chennai. I had one master's student. First, when we started working in healthcare, wireless, they were worried about security. So we came up with an elliptical cryptographic system, which was really powerful, but it took 5 minutes for the authentication. Who will sit in front of a machine 5 minutes for authentication? Nobody. So none of those crypto systems that we talk about wouldn't work at all. So we were looking at some continuous monitoring systems, and we used where you have to associate when it is in a home. You don't want to have 5 different sets of equipments. You want to use one equipment for all the 5 people in the house. So then when it is shared by different people, how do you know that the data that is collected is from certain individuals? Father, mother, child 1, child 2, child 3. So how to distinguish? So for continuous monitoring, we developed this protocol, which was really nice. It's my, we identified the taxonomy. We came up with a 2-layer authentication protocol, where we used ECG to ECG of the person to authenticate between user and the hub, and we used accelerometer data. So we fitted them with accelerometer data, so their body movements, so we use that to authenticate between node to the hub. So like a parent-child relationship we used. So we used the Alive heart monitor. It's from Australia. It's no longer available in the market. Then we used Wii Remotes for accelerometer. This is a bulky one. We could use simple tools. So my student fitted with those devices. We captured the data, and we used, again, machine learning algorithms to classify and then figure out if our algorithms, whatever we propose, it's working well. So we did test, and it did do very well. And then we added context information more to it. Proximity, distance between different nodes, so that whether the accuracy would improve, and it did improve. So we stopped with this. The student got tired. He got a good job. He wanted to leave, so that's where it is. But if you put in more context and more context, then it could become more and more accurate. So even this system worked really well, but if you build in more context, like certain hours, the way they live, the way they conduct themselves, if you build in more context, you can come up with more automated systems. So what we are now looking at is more into predicting and forecasting. It is not fun to pick up an elderly after they have fallen down, so you want to predict and you want to forecast certain conditions, emergency conditions. So we are using past data, now data to forecast. So we are using deep learning and other kind of unsupervised learning systems. So predicting as soon as possible and more accuracy, that is where we are gonna, and that is where the automation is gonna help. So automated technology for sure helps improve healthcare. Intelligent remote monitoring, it has brought tremendous improvements in chronic disease management and continuous health monitoring. But they do face challenges at data collection, communication, and security points. Choosing the right solutions, protocols, encryption algorithms, everything improves the quality of the healthcare as well as the healthcare costs. So automation is the key to the success of smart health monitoring and probably for our future healthy living. So with this, I thank you for this opportunity, and if you have questions, you're always feel free to ask me when I'm around. Thank you.
I would like to invite another keynote speaker for the day, Professor Radu Pradhan, University Multi-Objective Modeling and Optimization of Scientific and Industrial Application on Distributed Computing Infrastructures.
I'm Radu Pradhan from the University of Innsbruck, and I will give you a short overview of our activities on the multi-objective modeling and optimization of scientific and industrial application on parallel and distributed infrastructure, which is our expertise. So maybe you don't know where we come from. Austria is a small country in Europe. So this is the world map, and we are situated here, a very small size compared to India. Austria is called the country. It's a German-speaking country. And from Austria, I come from a small city. It's a mountainous city. It's called Innsbruck, and basically that's the place on the earth, if you're familiar with Europe, where it's located. It's famous for skiing and mountain activities. So the University of Innsbruck is one of the biggest universities in Austria. It has over 27,000 students, over 3,000 researchers, 64 study programs, 5 research centers, 4 research platforms, 33 research focus areas, and 306 partner universities, and you are among them. So from Innsbruck, I'm coming from an institute, a small institute of computer science. It's growing, so it has been founded about 10 years ago, where I also joined the institute. And we have 8 chairs, so 8 computer science chairs doing activities in the area of software quality engineering, databases, intelligent interactive systems or robotics, computational logic, mathematics, graphics and simulation, distributed and parallel systems, so here is where I come from, and security and privacy. So let's talk about our work in the distributed and parallel systems. I'm an associate professor there. The chair is Professor Thomas Faringer. And our team altogether has over 20 scientific team members doing research in this area. We are currently running a research portfolio of over 3 million euros, gathering our local university and external project funding. Among this funding, also projects in collaboration with India, which I will talk later on. Our topics of research are in the area of cloud computing, so distributed cloud computing, and our origin comes from high-performance computing, so here we concentrate nowadays on this modern area of many-core parallel processing. And in these 2 areas, basically, our keyword is performance. So we are system guys, and what we are doing research on is we work on trying to optimize the performance of your code. So this basically comes to our research interest. As I said, it's cloud computing. Here we develop a system that is also available for download. It's called Ascalon, an application development and execution environment for distributed computing infrastructure. So here we assist you how to program your application for clouds, for example. Then we have for parallel processing another project, which is called Insieme. That's a compiler. So basically a compiler that takes, for example, your C code and tries to bring it down with high performance onto your devices, whether it's a PC or a mobile device. Then we support many kinds of applications, mostly from scientific computing, but also from the industrial areas. And another more recent activity that we are carrying out at the moment is in the area of green IT. So we work on optimizing energy applications. So in brief words about these 2 projects, so Ascalon and Insieme. So Ascalon is this application development environment for clouds. Here we support the full development stack of your application to the underlying cloud infrastructure, which we try to hide from the programmer through the development of advanced middleware services. So here we cover from application design. So we work here with workflow application, parametric study, map reduce application, stream processing application, big data application. So all these hot applications you hear about, we try to integrate them into our toolkit. We have graphical and textual representation of this application that we support. And once you program your application basically in an abstract way, independent of the underlying infrastructure, we provide you a set of services that support you in running them with high performance. Here we have execution engines or runtime environments. We have schedulers that try to optimally map your application to find the best resources for running it. Resource manager try to keep track of the resources available and expose them to the application to understand their characteristic needed for optimization. We have modeling and prediction. So in order to optimize, you also need to know what is going to happen. And that's done through modeling and prediction of different parameters like time, energy, reliability, and so on. And everything works in a circle, so in a feedback-oriented loop. So the performance, the trace data is stored in a repository. So here we document everything that happens. And this is used again by the development tools to optimize, further optimize the execution, the application based on the execution history. So here we have performance analysis tools and also performance steering tools that we are developing. We work on parallel computers and we work on OpenStack clouds. And we also work with both real execution of the application and also simulation. So often the infrastructure that we really have available, it's kind of limited. We have supercomputers, but they are also limited in size and we have limited access to them. So in order to validate our method, you also need simulators. And that's what we are also doing through a backend of our system to a simulating tool. So the other project is Insieme, that's a compiler. So before you actually run an application on a distributed system, you also need to compile your application for the target execution platform. And that's done through another project that we are doing. It's called Insieme. That's a compiler for many core parallel architectures. So here we deal with programming languages like C, C++, OpenMP, Silk, OpenCL, MPI, and also extensions of them. And with what we are doing, we have a compiler and a runtime system that compiles, that translates the C code to the native runtime execution platform of the underlying running infrastructure. For example, we translate OpenMP, parallel OpenMP code to OpenCL if you have, for example, a GPU as a target infrastructure. So that's a compiler project we are running. So with India, we have two running projects. One is this in the area of energy efficiency for compilation of parallel codes. This is done with a small institute from Nagarcoil in Tamil Nadu. Our contact person there is Shajulin Benedict from Jean Xavier Institute of Technology there. It's a small private university. And another project we recently started, and that's why I'm here, accidentally because of that project. It's in cooperation with Tapa University, Professor Niraj Kumar. And here we also work on energy efficiency in the area of cloud computing. So we have these two running projects at the moment with cooperative project between Austria and India. Okay, so one of the major achievements that we did in our group was in the area of benchmarking. So we are system guys. So you heard two talks before and they had the good characteristics. They were very appealing. They did very user-oriented research. They did cognitive research. They work in the area of smart cities. You know, it's easy to perceive. But they don't mention one thing. They need an infrastructure, some service guys. Without these service guys, their research won't exist. And these service guys that sit in the back end, it's us. Yeah? And we do things like benchmarking, so you really quantify the performance of the underlying infrastructure that they need. And this is required, basically, if you want to operate with high performance, with good efficiency. And one of my major results was a benchmark suite that I did together with other European cooperators. And this is currently the Spec Cloud Infrastructure as a Service 2016 benchmark. Basically, we defined a benchmark for clouds, which basically characterizes the performance you are going to get for your application. This is required if you want to optimize that. And we published a paper in IEEE Transactions of Parallel Systems, a distributed system in 2011. And it gets a lot of citations. It's better than we ever expected. And it's in a scientometric analysis of cloud computing literature. Was classified as the 14th most influential cloud computing paper that we are doing. So we had an impact. And myself as the 11th most productive researcher in cloud computing. So we are kind of proud of this achievement. And it's in the area of benchmarking, and usually these are things you don't really want to see when you talk about research, because it's back-end. Okay, so one of the technical things I would like to talk today, because there are also many students here probably, so it's interesting, it's about workflow scheduling. So if you talk about, so workflows, it's clear what workflows are application represented as directly acyclic graphs. So you see this kind of large-scale infrastructure emerging, where you no longer program an application from scratch, but you take existing components and you try to orchestrate them in a meta larger application, which is called a workflow. So you can see these activities as existing legacy codes, and then you simply invoke them, and once activity is finished, you transfer the data to the next one, and so on. So this kind of distributed meta applications are more and more popular today. And one of the technical problems here is once you have such a workflow, and then they can get really complex, is how to map them on a heterogeneous infrastructure. You have a set of machines, distributed machines, cloud computing machines, and the question is, okay, how to optimize this application? Now, if you approach this problem mathematically, it has been shown to be NP-complete. NP-complete means that there is no polynomial, no algorithm with polynomial complexity able to optimally solve this problem. The problem is exponential, which means it's enough to have a small set of machines, a small set of activities, and really the complexity of the problem explodes with an exponential complexity. So you need to invent heuristics. Heuristics means approximate algorithm that find good solutions, but of course in polynomial time, and these solutions of course will not be optimal. It will be good. The problem gets even worse because we are in a multi-objective space. So traditionally you had one objective, time. You want to compute fast. That was the only metric you had. Now, it's no longer the case. Now you have more metrics. When you talk about clouds or distributed system, you see costs. If you go to Amazon, they charge you. And of course, the faster the machine, the more it costs. Yeah? You have also other metrics like energy consumptions, and it's the same story. The faster the machine, the more, probably the higher frequency it will have, and this will mean a more consumption on the energy side. Large-scale systems have reliability. The more computers you have, the more unreliability you introduce into the system. Systems will fail. Storage, it's another one. Robustness, utilization, fairness, in general quality of service. So you'll end up into a multi-objective space. And what's the challenge here? There is no more single solutions. It's always about compromising. You compromise one objective for the other. So in this case, I show you a compromise between time and cost. If you work on Amazon, for example, the faster you compute here, the faster you compute, the higher will be the cost. The slower you compute, the cheaper will be the price, the cheaper will be for you to compute. So the trade-off is, the question is, what is your trade-off here? The trade-off is, in multi-objective optimization theory, a curve, and this is called Pareto frontier. And the challenge of our algorithm is to approximate this Pareto front. Now, if you look at the Pareto front, you see these green points. These are called dominated points. These are points that are worse with respect to both objectives. So this is where you don't want to be because you compute slower and more expensive. And these are unfeasible points. So this is the ideal world that usually you don't have. Computing fast and cheap. Yeah? So what we want to approximate is this blue curve. This is called the Pareto frontier. And then from this curve, the users usually can select the set of trade-off solutions or the trade-off solution that suits its budget, its computational needs, and so on. For this, we also designed an algorithm which is called multi-objective heterogeneous earliest finish time. Heft, multi-objective Heft algorithm. If you are familiar with scheduling, you know probably Heft. We extended this Heft algorithm to the multi-objective world, and it's another quite well-cited work that we did in our group, and it had some impact in the community. Now, I prepared you a description of the algorithm, but I will skip this because of time limitations, so you just have to get the message. Within this exponential space, we designed a heuristic with polynomial complexity that approximates this Pareto optimal set of trade-off solutions. And I will simply skip the result of this optimization problem is such it's the Pareto optimal set, so the set of Pareto optimal solution that approximates this trade-off between cost and time for computing an application. So we designed this algorithm and we evaluate it in various contexts, for example, for approximating the trade-off between time and cost, between time and energy, between time and robustness, between storage and reliability. And we pick many kind of such objective combinations. We do the evaluation in clouds, in private clouds that we have in our infrastructure, which is based on OpenStack. We also go to commercial clouds like on Amazon, GoGrid, and Rackspace, and many other hybrid cloud infrastructures. We have real-world workflow, so we work with real scientists that have their workflow applications. And we also have some simulated workflows if you want to evaluate on some workflow structure and complexity problems that are not easily reproducible in real life. So as I said, a combination of this simulated of synthetic workflow and real execution workflow of real-world case problems. So just to give you an example, one workflow we are running is this rain cloud workflow. So we live in Innsbruck, that's a mountainous city, and maybe it's not a fashion in India, but in Europe, people look for adventure. So they like to go in the mountains unprotected, yeah, like people go in Himalaya. And of course, there they are exposed. And they rely on this, on the forecast service that is come from a center, European Center for Medium Range of Weather Forecast. So basically, they rely on forecast about the probability, the danger of avalanches, yeah, for example, in winter, of floods in summer. And this center has to provide this service with a certain regularity at certain times during the day with a certain frequency. And for this, they developed a workflow that does this prediction, and this workflow has to complete by certain deadlines. So depending on the budget, depending on the frequency that they have to deliver this data, they rely on us to schedule, to run the workflow so that we finish it by the desired deadline to provide this reliable prediction data to the adventurers and also to fulfill the budget, the computational budget that they have from the state in this case. So some of the results that we achieve, so we approximate this Pareto cost trade-off, in this case for running in a cloud, and you could answer questions such as, by increasing your make span, so make span is a synonym to time, so by increasing your computation time by 7%, by intelligently selecting your cloud resources, you can achieve 50% of cost savings. Yeah? So just by being smart enough to concede 7% of time, you could halve your budget consumption. Green computing is also very hot. We want to be environmental friendly. So we also had work that is done on approximating the energy versus time trade-off. So here we did more simulation for different kind of workflow sizes. So one of the answers that we have here is that it's even more impressive. You can achieve 80% of energy savings by selecting energy-friendly machines with only 8.2% make span increase. Or for larger, so the larger the workflow, the larger the benefit that we had. So 3.3 make span increase by 85% energy saving, and so on. So these are important questions that we expose to the system and application developers. And this has been awarded recently in one IEEE ACM conference with Best Paper Award. It was a very selective conference with 18% acceptance rate. Okay, I have more results here, but I don't want to go into too much detail. So here shows another experiment that we did which tries to optimize for robustness. So if you work on clouds or on this distributed computing system, you have fluctuations, yeah. You send once the application, it will take 10 seconds, the next time it will take 20 seconds. Why? Because there are lots of variability in the resource performance, because of the distributed computing infrastructure, because of a lot of external load factors. So here we did another work that tries to optimize this robustness. So they try to minimize the variability. So we select the resources that are very predictable in this case. So we show what is the trade-off in computation that you have by selecting from an infrastructure the resources which are more reliable in terms of predictability, so that they don't have such a high fluctuation in performance. Good. The work on storage I will skip because of time limitation, but it's another work that we do. We try to optimize for storage. I will try to reserve the last part of my talk to talk about an industrial application that we are targeting. So we will not only to work with scientists, we also work with industry. And believe me or not, we found interesting scientific questions to solve in the area of gaming. So gaming, I think many of you would lie if you tell me that you don't play games. I think most of us, at some point during the day, you play this kind of entertainment applications here that somehow free your mind or give you some leisure, some time to relax during the day. They are massively multiplayer online games, and they are a very important type of application for the industry. So if you look at the growth of the different markets, we see that the gaming market is growing at a 6.6%. So that's the rate at which the game market currently grows. It is projected to be an almost $120 billion market by 2019. So if you compare the growth of the other markets, you see that only the internet market, the overall internet market, grows at a higher rate than the gaming market, 7.1. The others, even TV, video, music, cinema, books, grow, but at a lower rate. So it's an exploding market, and basically you also work with gaming companies in the area of operation of multiplayer online games. Before coming here, I was Googling on the Indian market, and I was surprised to see how large it is. So here you see the numbers. So it's a $200 million market with a projection of being 1.1 billion by 2020. And if you look worldwide, you see India being on 5th place worldwide, and it's growing compared to the Brazilian and Russian market, which are currently above India, but they are kind of decreasing in comparison to India. So India has a huge potential in the area of multiplayer online games. What is interesting about games, so why games are not only about shooting, that's the user side again, which other researchers are currently investigating. We work on the system side. So on the system side, basically, if you connect multiple, large thousands, millions of players all together, and you map them into such a virtual world where they can interact together, the interaction between different players generates load. Load that basically has to be hosted, processed, and basically accommodated by the underlying infrastructure. Massively multiplayer, a player working in interacting with massively multiplayer online games basically has to first send the actions to a game server. So it's a client-server model. The server has to process all the actions, collecting items, shooting, moving around, process this interaction, and then delivering back to the clients. And this has to happen with a certain update rate. And this can be very high if you want to have a responsive game. It can be up to 60, 100 hertz. So it means 100 times per second, the server has to process to receive the commands from every player, process them, compute the new state of the game world, and then broadcast back the new state. And if you are not operating at 100 hertz, the players, basically, we experience an interrupted environment. You will shoot someone, but the action of the server, the impact on the virtual world is not what you're going to expect. So they are very, very sensitive. And this basically requires high-performance computing, requires a high-performance infrastructure able to really process and accommodate all these players. If you are not fast enough, you will be congested. Congestion means fragmented play, not responding to your actions. And there are two types of demands that we are trying to accommodate, the long-term demands and the short-term demands. And long-term demands are games that basically evolve, have higher success that they can actually expect. So we have seen really games like World of Warcraft that has an exponential growth in the number of players that they have, and the companies have problem really provisioning the resources, purchasing the resources required for hosting all the gamers. And also during the day, so the short-term demand, which has peak hours during the day and off-peak hours during the night when people sleep and don't play. So if you want to provision the optimal amount of resources for such application with a variable demand, then of course you need clouds, yeah? So that you can project the game load onto the future through prediction techniques, and then on demand allocating the right resources through purchasing, renting of resources from cloud infrastructures. So that's basically what we did in our group. And we deal with techniques such as parallelization of game servers. So we try to split game worlds into multiple sub-worlds and put them on different machines so they can be operating in parallel. We try to model the load. So we try to understand how many gamers are playing and how much load they need from the infrastructure. We try to provision the cloud resources for that. We try to offer them the quality of service. And of course, through service level agreement, also charge them, so project them into business models. And what was surprising to me is how much of this stack is also required for scientific applications. So if you look at scientific applications, basically, they follow somehow the same software stack. You parallelize, you model the performance, you provision the resource, you provision the quality of service, and then you end up with service level agreements. So again, I'm not able to provide more technical details because of technical limitations, so I just want to thank you for your attention, and I'm taking questions if you have.
Thank you, sir. I would like to invite another keynote speaker for the day, Professor Sneha Anand. She has contributed her 43 years of her life to Indian Institute of Delhi. Her principal achievements are in the areas of transducers and biosensors, reproductive bioengineering, and rehabilitation engineering. For her scientific endeavors, National Research and Development Corporation awarded Topmost Invention Awards for the year 1989. Ministry of Welfare presented Technology Invention Awards for the years 1988, 1989, 1992, and 1993. In rehabilitation engineering, and the Indian Council of Medical Research conferred Kashnika Oration and Citation Award for the year 1993 in healthcare technology on her, and many more. With this and others, Professor Anand stands unique in the country as an engineer who has gone beyond academics and practically helped people through biomedical technologies.
It is my very great luck that the biomedical engineering started when I finished my master's in electrical engineering, and that is why we could, and it is a joint program of All India Institute of Medical Sciences and IIT Delhi. So practically everything that we do in research is validated at by the medical faculty. And this is, we have done research work for preventive healthcare, diagnostics, treatment, and rehabilitation. And as I've shown the slide, which shows IIT AIIMS joint program, and it is my luck that it started after I finished. And see the optimal solutions which which give you the healthcare concerns and minimize the value of delivering affordable solutions to for the treatment of any person who is suffering from any disease. Okay? And that is, if they are critically ill, then how to make the proper monitoring of the body, and so that it is actually it is used, and so how the scientifically validated physical, emotional and mental health by EEG and other data. You will see the technical aspects. See, here we are lucky, as I have shown, we have the basic foundation of engineers and doctors is to see what is the physiology of the body is very intelligent. Isn't it? The body physiology is very, very intelligent, and it works according to your own interest and work. And it is working in technology and medical, and how to create the sensor, so that how my body is needing, what need, it gives automatically to that one. Okay? And that is what the science and electronics and mathematics works in the body. So healthcare is a very, very, body works in a very, very intelligent computer manner, and CPU, each one of us has a own CPU. Next slide. And this is how the human body physiology I have shown works in a totally different, reproductive system works in a different manner, respiratory different, and all the other body. I would like to share all the slides, all the younger generation to take the things forward. Okay? And I would request all the speakers' slides to me. So this is whatever the work is on. So it is a multidisciplinary work, as I have already mentioned. Next slide, please. And that is what it shows, how the biocomplexity is, a biomedical works in a very, very complex area, and you can see the atomic work, molecular, cellular and tissue, and how the organ organizes the work that I want to do. Supposing I want to speak something, automatically the tongue and other respiratory system will give you the technical input. Next slide. And that I have already mentioned. So this is how the brain needs intracranial pressure. We have done the work on very good technologies to monitor the intracranial pressure, surgery, how to do cardiovascular, thoracic, rehabilitation and other areas of research, which is technically transdermal drug delivery also, so that you don't have to give injection, automatically the thing is given by and this is how first you have to understand how the body is needing, what is the need of it, and what is the research needed, and how to find the solutions. And this shows how the work has been technically validated and worked, learning and developed technologies. Go next slide. Your own network, you can see, is a very, very complex network in your CPU. When I'm talking, automatically it will give the signal to the part that I need to speak this word, or that word, or where, what I want to project. It goes in a totally electrical, very good electrical network, goes in that manner. Okay. And this is how the technology works in optical, chemical, all types of engineering works in that one, mechanical, electrical, computer, fluid mechanics, everything is needed in the body, and it works in a very, very good manner. And how your eyes need, how the reproduction needs, how the brain is needing what next, rehabilitation and others. That will be very nice. And see, the body is a very, very, you can see, very, very complex system, isn't it? If I'm eating something, what kind of food is coming and how it has to be processed, it goes into your intestines, what is to be thrown in the liver, what is to be thrown in the kidney, what is to be thrown out, it goes automatically in that. This is very important, what already she had mentioned, that is the cost-effective solutions for mass healthcare, and monitoring is done in the body. Look, this is what is the stretcher, which any patient that has to be carried from staircase, anything that can be carried. This is patented and it is now practically used across the country. Okay? practically used across the country. So that you can see up the staircase, and this is the weighing machine which we have made, where the adult and the baby both can be easily weighed, and it is now practically used across the country in mass healthcare. And this is a kit which she had also mentioned. This is a healthcare kit which is portable, which has a electronic data logger, blood pressure monitoring, everything is flowing, and it is a kit which the health worker carries in the bag and takes it to every house and collects the data and brings it to the our units. You know, we have the primary healthcare centers in all the villages. So he or she carry the information about every patient and brings it to the doctor. So that primary health center, it is brought to the doctor, so the doctor knows what the medicine should be given to the patient, okay, across the country. And this is very interesting work which has been done in monitoring the plasmographically, PPG and other things, so that the whole body reflects everything. And I had mentioned in the morning that anyone will agree, mother catches the fly, because she brings us up. She is the one who brings us up, takes it out from the womb. So electrically we have done, and instant ECG has been monitored from the patient across this thing. And this is a Zigbee, which is put on the chest, and the ECG data goes to the doctor anywhere that person is. So there is a kit there is a chip which has been made, put on the head, on the heart, and it goes across that. And this goes feto-maternal monitoring, neural correlations, and photoplasmography for for so many clinical. And then we have done so much work on the anesthesia monitoring, whether the person needs the pain index and the other index, so that they get the medicine accordingly. And this is adaptive leg which has been patented, which is the go one back. How to monitor the gait cycle of every individual, so that the artificial leg has been made, which can be taken to the automatically to the patient, whosoever needs what. Okay, so which area of the muscle or which area of the bone is not working properly, so that it is taken forward to that one. You can see the muscle as well as this thing, which are the markers, as it was projected earlier also, so that you can check which part is not working properly, so that from foot to body, and the brain is the one which controls the movement and other things. And this is the proper gait cycle. Next slide. And this is weight carriage. And this is how the electrical plasmography taken on the leg, which is the part of the, this thing. Your knee joint is not having proper functional, because you have this thing, proper molding is needed for the problem. And this is what I've shown, how to carry, how the weight carriage is done, and how your back, the student should not carry it on one side, they should carry it in a balanced manner, so that the the back problem is not there to them. This is what is. And this is, I've already mentioned, this is what we got, this thing, and that is the anesthesia monitoring on all patients in the hospital at the medical institute. Okay, to monitor the pain index and whether induction has to be done, on what basis, accordingly the chemicals, this thing should be conducted. And this is what I've already mentioned, they monitored the blood pressure, heart rate variability, and anesthesia is reflected in that one, so that whatever disease is there, EEG index shows, and then it is reflected in that one. Next slide. And this is what is the electrical, this thing, how the respiratory and the cardiac system balances the pulse index and other things. and external counterpulsation. This is now used in the medical institute. That is, bloodless surgery chamber has been made, and so that the principle is that so that we have made a blood external counterpulsation alternative this thing, so that whatever surgery, when the surgery is going on and the like, no blood should be good. So in the bloodless surgery chamber. Next slide. Next slide. Okay? Now it's okay? And this is the BCI, brain computer interface. Whatever I want to use and do, it is electrically. Whether I want to pick something or I want to move this hand, that hand, what? So it automatically does that. It automatically does that. I want to call somebody or I want to do, so electrical, it is done, all validated at the medical institute, too, by electrical plethysmography as well as by photoplethysmography. And this is the computer for the blind. So the touch pad, now they are used across the country. They have become teachers they were in the Blind Relief Association in Delhi, and now across the country they are teachers and everything. They are working on this is a touchpad, this thing for word editor, doing anything that you want to do to type, so that they are able to read and hear and write anything. Okay? This is the brain works in a very, very intelligent, all engineering work from science, mathematics, and everything is in a very, very intelligent manner. And this shows the recognition by brain oscillations to know whether I am watching a face, whether I am watching a building or whatever it is. Next slide. And this shows how the frequency of the brain. And this is what is the blow switch for the people, for whether I want to do whatever I want to do, left, right, up, down, so that you design something so that it works. I want to do this thing, then it automatically works on that one. Okay? Neural correlates that are with visual recognition. Okay? How it is technically validated. Sight. And then we worked on the Nadi Yantra developed here, so that it gives complete information about the disease, which was there long back. People, jitne bhi ancient people, Indian the, they used to touch and tell you what is the disease that you have. So the body index works in that manner, and that is what I have validated at the standard signal from radial artery, how the tidal volume and other things are changing, and which one is changing, so that they can know what is the problem that is occurring, and how the thing change with the different signals that are captured. Okay? All validated at that. This is how the signal has been acquired after eating, because they say whenever you come for the disease monitoring, you must come empty stomach. You must come empty stomach. Jitne bhi vaidya hain, Ayurvedic vads, they will say don't come for this thing without. So this is before eating food, and how after eating food the signals are changing. Next slide. I'm almost. Variation in the Vata, Pitta, Kapha. These are the three parameters which are reflected in your this thing, and that is what they say, that which are the points which are changing with after eating food and before eating food. And this is what we have optically based data acquisition system for this one, for this only. Okay? And when I'm doing yoga, how the yoga is helping in taking the PPG data and showing how we are balancing our body. Okay? Balancing the body. And this is how they are monitoring what I said by this thing, what is the disease that you have and what is the problem, and they monitor from this one. And that is the psychoneuroimmunology that is reflected from your brain to the body. Okay? And this is how the intelligent system works, and how the electrically signal. When I am balanced, then the alpha rhythms are in the green area, and then they show I am totally mentally not stressed. When I am stressed, then they go to the red area. Okay? All validated at that. Electro-optically monitoring this is your CPU. Ajna Chakra is in the center, and this is the master controller of the body. Master controller of the body, CPU. Okay? And that is where how it is physiologically taking care of the ECG, PPG and other things, so that there is a balance in the complete body. And how the respiratory sinus arrhythmia is giving a balance after doing the yoga and other things, all validated at that. Autonomic balances that take place in the body by using the yoga and Om chanting. Om chanting also helps a lot in bringing the, go one slide back. See how the baseline structure, which madam was also reflecting, and this is the this thing, and how when we do Om chanting, how the balance is taken by the taken in the body. Om chanting is a very useful this thing for taking the balance in the respiratory end, and this is the biomechanics of pranayam. How I am taking deep breath, and it is controlling the whole system of the body. This is what I have already gone through. And effect of the music, meditation and arithmetic task. There is a big changes in the brain EEG structure that is taking place. Okay, you can see the algorithms that have been developed and monitored in the in all. Right nostril is dominant, then the left one. When I am doing this, then this is a very good this thing, which is GDV, galvanic discharge visualization, and that is why I said all of us know the mother catches the lie, mother takes no, and because she does, she catches us and all, and this has been validated. Electromagnetic signals, how they are transferred from the brain to the body. And this is Ajna Chakra, this is how the body reflects the electrical signal from the body, and this reflects all diseases that are there in the body. All diseases are reflected in the body by this one, fingerprint, all fingerprints. Okay, yes, this is how each fingerprint, what part of the fingerprint is reflecting what thing. Okay, this is very well validated at the All India Institute of Medical, and this is galvanic discharge visualization. That's how the teacher and the student interaction, mother and the child interaction, and friends interaction, two friends and two enemies, how they see each other and how this will change automatically. Automatically. This is before meditation, after meditation, and after meditation, and Sudarshan Chakra. This is what I have already mentioned. Go forward. Go forward. Go forward. Go forward. So now it is computer-aided diagnosis for reducing the shear waves and other breast cancer detection. Okay, we are doing that, and this is completely all used in the across the country for the rehabilitation, central lathe for the blind. Okay. Now it is used across the country, okay, and this is the artificial leg which we have developed, and we've got the international awards also on this work. And this is what is the reproduction work, that is how to monitor how the mother's this thing goes into the how the ovum is coming, the egg is coming from the body into the ampulla and other body, and then the sperm goes from the down to back, and how electrical field prismography reflects the baby movement and the baby going, how we have done that ultrasonically, and that's what I've already mentioned. The ICP, intracranial pressure, is monitoring whether respiratory and cardiac activity, and medical institute had validated on all subjects, and they could detect all the diseases, and which I've mentioned to you, the healthcare kit that we had made is actually validated in all villages across the country. How the environmental system helps you to keep the body healthy and happy. Okay, and this is how I would like to say the health is very, very significant. If you walk, work, and work with interest, then how the everything goes in the right direction. Okay, goes in the, there are many things which are around to help you to stay very, very healthy. Okay, what is the hazardous which you don't like? If you don't like what you want to do, then your body will not work properly. And this is a thing which we have done, that is how the ear, how when we are using the mobile phone very long time, how which part of the cochlea is having a problem. And electrically it is going into the head, and then it is going into the brain. The cochlear cell moves, vibrates to give the signal into the, how the mind and body works. If I like something to do, then your things will work very, very well. How they work brain and mind. If I am interested in doing something, then the work goes in a very, very positive direction. Okay? Very, very positive direction. Your brain will work in that. Now the sensory inputs and brain computer interface I have already mentioned. That is how we have monitored. That is, I want to do this thing, and automatically you are monitoring, and then you are taking peripheral blood flow changes according to what I want to do. And EOG analysis, that is, I want to do what processing I want to do, left, right, up, down. So it is computerizing left, right, up, down, so that I want to do this, automatically the system will work on that one. And this also, whether I want to do the wheelchair control, whether I want to move, or anything. And this is the rehabilitation work that we have done. This is for the spastics. What I want to work on the spastics, okay? And how the blind are needing help in reading, writing, and doing anything. Okay? We have done that, which part is reflected, and how to make the speech graphic dynamic biofeedback trainer for the editor. Left, right, up, down, 6 start metrics, and we have done that. Next. And this is the blow switch, which I want to do this, I want to do this, then automatically it will do what I want to do that. And this is the age, sex, and BSA, so that monitoring depth of anesthesia in the hospital. Okay? Non-invasive, go one back. Non-invasive continuous blood glucose monitoring is being done, non-invasively. Okay? That is, the principle is, that is done in a signal that is coming from the skin and alternately monitored by the other one, invasive and non-invasive monitoring. Okay? And this I have already mentioned. I have already mentioned this. Electrical impedance prismography reflects many things. Next. Fetal-maternal monitoring, and I have already mentioned. If the baby is crying of hunger or anger, then you know from the signal, that is the HRV changes that are taking place in the body. Okay? Now, we are in the final stage that I have already mentioned. This is the principle of external counterpulsation, so that, yes, go forward. Body, mind, and soul. As I have already mentioned, it is physical body, and how the software, alternative medicine is working on that one. So, next slide. So that your brain and how the body and brain are bringing the balance in the working conditions. Okay? So that you can see the influence of physiological system, modulation, and cardiovascular system measurements, which will reflect how the system works. And when I am running, when I am sleeping, when I am doing, how the RR interval and other things, they change automatically. Sympathetic and parasympathetic system. When I am taking a deep breath, when I am taking a slow breath, how the balance is going to take place. Okay? And psychophysiologically, we have monitored various aspects of parameters, EEG parameters, ECG parameters, PFT, and parameters. And this is how EEG is reflecting, the balance is coming as we have done the yoga and other things. It reflects that. See, after 6 days of pranayama practice, how the EEG signal is coming to the balance. And see in the next slide, which shows 55 days of pranayama, and it is going to mode balance. It is going to mode balance. EEG. Next. Dynamics of the brain is according to what I want to do. Accordingly, it is showing the spectral power of the body. And this is what I have already told. This is the Ajna Chakra, Om chanting and other things, how they are reflected. When I am not happy, when I am happy, how the spectrum is changing. Next slide. Very, very important psychophysiological assessment is done by pranayam, Sudarshan Chakra and others also. Lifestyle management, depression should be decreased, anger should be decreased, and lifestyle management should be increased. Do not stay in the stress management at all. Okay? Don't get stressed for anything. Okay? Next slide. I'm towards the end. Pranayam. Yeah, this is what is electromagnetics coming from the body. Okay? And this is reflected very well in the showing how the signals are affecting this one. When I'm doing something, spectrogram of the sound vibration in yoga. And this is what is reflected in your all fingers, optical thing analysis. This is what I've already, 5-finger PPG. Photoplasmography, that means blood flow changes. And this we have made a device which reflects this, what I've mentioned, by the electrically, Kirlian photography, which I've already. The device has been validated at the medical institute to give the shape. Okay? What is spondylitis, cardiac arrest, whatever, it is coming from this 5 fingers. Okay? It is reflected by that one. And almost your pressing of the foot and finger, how the hand, how the feet and hand give the map of various parts of the body. Various parts of the body. And this has been bioX mapping, and it is reflecting the array of sensors which will reflect. If you press here, then the which part of the body will get into the various aspects, which we have already validated. Okay? Which has been analyzed during which type of yoga and analysis. Okay? Right nostril, next Nadi Yantra will reflect that. Okay? Which I have already mentioned. Okay? Screen. Okay? This is what I have already shown. Okay? Sympathetic and parasympathetic nervous system, and this is showing the effect of the music and meditation, how the changes are taking place. Go just one slide back. I'm finishing. These are the biosensors which we have developed and validated, glucose monitoring and the hemoglobin monitoring. And now the electro-optically hemoglobin monitoring, next slide and last slide. A drug delivery through the transdermal. If I want to give the drug, then electrically it can get transmitted into the body, don't have to give any injection. And this is non-invasive diagnostics in the through the saliva for taking the sugar level, electrochemically, optically and medically. We have done diabetes in all patients at the medical institute. Just they're throwing the saliva and we are getting the glucose level. We are getting the glucose level by that one, and by the analysis. Last, we are, okay, and this is developed prototype system which is now patented. Which has been patented, and the student has got the, under me, she has got the award. She has got the award on this work. We have developed the prototype system. I'm towards the end. Thank you.